In this video we discuss sets and operations. So after finishing this video we expect that you will know what the set is and how to express it, and to perform operations like union, intersection, and complement on sets, and to use Venn diagrams to illustrate sets relationships, and to know properties of set operations. So let's start with the following scenario. Selma is 3 years old. Her parents just started teaching her the English alphabet. In some stage they prepared flashcards with some letters from English and other symbols to test if Selma can recognize the English alphabet. The parents will correct Selma's wrong answers. So, for example, the first card may have the letter A on it, here B, here $, here C, percent, the percentage or percent sign, K, M, T, W, plus, and multiplication, and X. Let's call this X. Okay, so we want to first name the above set of letters and symbols. Here, if we look at this is not a set of letters because it includes some symbols, and it's not a set of symbols because it includes letters. So it's not easy to name this set. But if it consists of English alphabet, then we call it set of English alphabet. But this is not a set. This is not a set. Can you determine which symbols belong to the set of English alphabet? So in general we're talking about set of English alphabet, but this set is not, this collection is not a set. Now we want to consider the set of English alphabet, and we want to determine which symbols belong to that set from this collection of letters and symbols. The first one, A, belongs to the set. This belongs. B belongs. $sign does not belong. C belongs. The person sign does not belong. K belongs. M belongs. T belongs. W belongs. The plus sign does not belong. X belongs. So we can determine which elements belong to the set. Good. Now, what do we mean by a set? A set is a collection of a well-defined, it's a well-defined collection, let me write it this way, it's a well-defined collection of distinct objects or distinct things. So what do we mean by well-defined? Well-defined, we are talking about set of English alphabet or English language letters. So this is well-defined. Why it's called well-defined? Because you can determine whether a given symbol belongs or object belongs to that set or not. For example, the $sign does not belong, but B belongs. So if we can recognize which element belongs to that set and which does not belong, then we call the set well-defined. And then it's collection of distinct objects. So distinct objects, that means A is different from B, and so on. C is different from C, E different from W, and so on. So we have distinct elements and the collection is well defined. And actually this is just a description of a set. We don't have a definition for set, because if you say set is a collection, what does collection mean? Collection means set. So we have a cycle of definitions, and this is endless thing. So endless process of naming things. So set does not have a definition, but it has a description. This is a description of the set. Okay, so the two important things are the set is well defined and it has distinct objects. Now we can write a set in two ways, either in raster notation. What does that mean? That means we list all elements of the set. For example, if we're talking about English alphabet, we write A, B, C, D, E, F, G. I mean to write all elements of that set. And how to write the set using this notation? We use braces, as you can see here, and inside them I should write them this way. They look like this. So we need to put the elements inside this, and between any two elements we should put comma. As you can see here, we have a comma here between AB, comma between BC, between CD, and so on. So, and here we listed all elements of the set, but sometimes it's not easy to write all the elements, and the set is well known. So for example, here we have all these elements of the set, but if we just describe the set, if we say that, let's consider X, which is a variable, is an English letter. So if we describe the set this way, and let's call it E. So the set E is all X, where X are English letters. So it's X, the elements inside it take the form X, or can call them X because X can be A. For example, let's choose A. So we have A such that A, now those two dots are denoted or read as such that. Okay, so if we plug X for A for X is a variable, so if X is A, then we write A such that A is an English alphabet or an English letter, and that's correct. And same thing for B. B such that B is an English letter. C such that C is an English letter or English alphabet. And that means this is true for all letters, English alphabet or English letters. So here in this case we describe the set using a new notation that's based on some variable X, such that X has that property, English letter, this is the property of X. So this notation is called set builder notation. Now consider a set of all natural numbers from 1 to 6. We want to write it first using raster notation. So raster notation, that means we list all elements, and it's better to name that set. Let's call it E, and we usually use capital letters to denote sets. So E is equal to the set of natural numbers from 1 to 6. So we write 1, 2, 3, 4, 5, and 6. And if we want to write it using set builder notation, we write X such that X. What is X? X is a natural number from 1 to 6. Now this is a very important point about the notation. We denote sets by capital letters. We can call it A, B, capital letter, E, any English capital letter. And we call, for elements, we use small letters like A, B. This is in general what we do. Okay, but here this is just an example. For just purposes of the example, we wrote them as capital letters, but we should, in general, we should write them as small letters. Okay. Now, when writing set, this is just a summary. Repetition of elements is not allowed because that's meaningless. Because if I write here in this set 2 twice, 3 twice, or 3 times, that will not be helpful in understanding the set, or that will not add any added value to that set. So still the set of natural numbers from 1 to 6. So repetition is not allowed in the set. And the second thing, order of elements doesn't matter. I mean, if I write 2 before 3 and 2 before 1, that will not affect the set. It will still stay the same set, same elements. So order is not important and repetition is not allowed. Now, membership. What do we mean by membership? If we have an element, we denote it as small letter. This is an element of a set A, so we write A belongs to A small belongs to A capital, and we use this notation. This is read belongs to. And here, if A does not belong to a set A, then we write A does not belong to A. Okay. Now, set equality. Now, we call two sets equal if all elements are the same in the two sets. So here we have, for example, set A consists of A, and A is still in B. So this is first thing. Second thing, E and A correspond to E and B. I and A correspond to I and B. O and A corresponds to O and B. And U and A and U and B. That means those sets are equal. Even because we mentioned that order doesn't matter. It's not important. So this means the sets are equal, and we write A equals B. Now what about C and D? As you can see, 2 is in C and it's in D as well. 4 is in C and it's in D as well. 7 in C and in D, but 5 is in C but does not belong to D. So C is not equal to D. We write C not equal to D. Okay. But instead of that, we can write D, because all elements of D are elements of C. So D is subset of C. We use this notation. This means subset of, or read subset of. So D is a subset of C, but C is not a subset of D. And you need to notice the notation here. So this is the notation that's used for containment. And as we can see here, A is a subset of B. If every element of a set A is an element of a set B, then we say that the set A is a subset of the set B, and we write A contained in B. Now, an example 2, we want to consider set an example 1, and we use the containment simple to express the relationships between A and B. Now, A belongs to B because everything in A every element of A is an element of B as well. And B is in A because every element in B is also element in A. If this is correct, then we write, if A is in B and B in A, then we write A equals B. So two sets are equal if elements of the first set belong to the second set, the second set, and the elements of the second set belong to the first set. I mean, elements in the first set are elements of the second set, and elements of the second set are elements of the first set, and we write A equals B. And for C and D, we notice that C is not contained in D, but D is contained in C. This is contained or equal, and we don't have any problem if we add equal or remove it. If we write it this way, that's fine, but we usually use this containment with equality. Now we want to find 7 different sets of the set A equals 1, 2, 3. We want to find subsets. How to find subsets? We start with the first element, so the set that consists of 1, the set that consists of 2, the set that consists of 3. Those are 3 sets. Can we find more subsets of this set? Yes, we can take 1 and 2, we can take 1 and 3, or we can take 2 and 3. So how many sets are there? 1, 2, 3, 4, 5, 6. Or we can take the same set, 1, 2, 3. That means 1, 2, 3 belongs to the set A, which is 1, 2, 3. So we have 7 sets. But is there any? Yes, because you can just choose nothing, and that's called the empty set. Empty set, and that's denoted as phi, the Greek letter phi. So phi is subset of every set, because you can just put your hand in that box and you don't choose anything, and that means you get an empty set. So how many sets are there for the set A equals 1, 2, 3? There are 8 subsets of this set. Now, how to determine this number? We can use a formula for that. Number of subsets of a set is 2 to the power n. N is number of elements of the set. So here 2 to the power, how many elements are in the set A? 3. 2 to the power 3 is 8. So we have 8 subsets, and so on. So we can apply this for any set, any given set. I mean any finite set. Now empty set, the set that contains no elements is called empty set, and it's denoted as phi. We may write it this way or this way. Okay. Now here's an exercise. The set 0. Now this is not empty set. The set 0 is an empty set. This is not empty set because this is a set that contains an element. 0 is an element, but the empty set does not contain any element. This is empty. This is not empty because it has the number 0 in it. So this is a false statement for this reason. Now the set is subset of, the empty set is subset of every set. That's correct, because as we described, so this is true, because as we described, you may choose to not to pick any element of that set, and you get an empty set. Now how to visualize sets? You can visualize sets by using what's called Venn diagrams, and those were invented by John Venn in 1880, English mathematician. So what do we mean by a Venn diagram? Venn diagram is a diagram that's used to represent relationships between collection of sets, and we have a universal set. So we start with a universal set. This box is denoted as U, and that means the universal set. All sets are belong to that set, and the elements are sets. For example, the set A is a subset of the universal set U. For example, the set A can be ABC. So ABC, the set ABC is subset of all English alphabet. The English alphabet is called U, the universal set. Okay. Now for the following Venn diagrams, use containment notation to express the relationships between the sets and A and B. So here, let's look at the first set, the first Venn diagram here. The first Venn diagram. Look at this. A is the same as B. This circle denotes A and B. So A belongs to B, or subset of B, sorry. Belonging notation is this one, and it's used for elements and the set. The relationship between an element and a set. So here A is contained in B and B is contained in A because those are equal. Now what about the second set, this one, this Venn diagram? We notice that A belongs to B. As you can see, A is in B, but B does not belong to A. B is larger than A. It contains more elements. Now what about the third one, this diagram? For this diagram, A is not contained in B because there are some elements of A here that do not belong to B, and there are some elements of B that do not belong to A, and only these elements here between A and B that belong to both A and B. So B is contained in A. Now what about the last one, the last diagram, Venn diagram? A does not belong in B and B does not belong in A. They are disjoint. They are called disjoint. We don't have anything in common. And here, this is, in this one, we have, in number 3, we have some common elements here. Okay. Now we have this introduce us to the set operations. So let's start with the union. So let A and B be two sets. The union of A and B that is denoted as A union B is the set of all elements that belong to either A or B or both. That's the union. For example, if we want to show the union of those two sets in the first diagram, this is the second, this is third diagram, this is A, this is B, this is A, this is B, and this is the universal set. Okay, so here, what is the union? The union is everything in A, all elements of A, and all elements of B. So this is the union. So all elements that belong to either A or B or both. Now what about the number 2 Venn diagram, or diagram number 2? What is the union? The union is everything in A. That means we put all the elements together in one set, and all elements of B. So the shaded region represent the union. What about C or number 3? The union is the set B, because we have B and A inside B. So when we take the union, we still have all elements of A and B are elements of B. Okay. Now let's take an example. If A is 1, 4, 9, B 2, 4, 7, 8, we want to find A union B using raster notation. A union B, that means all elements of A, 1, 4, 9, together with elements of B, but the repetition is not allowed. So we write 2, 4, 7, 8, but we notice that 4 is written twice, so we need to erase it from here. And that's it. This is using raster notation. How to write it using set builder? We can write X such that X belongs to A, or X belongs to B, or both belongs to both of them. This is how we write the union. Now the second operation is the intersection. So let A and B be two sets. The set of elements common to the set A and B is written as A intersect B, and this is called intersection of A and B. So let's do these exercises. So we have, this is set A, this is set B, and this is universal. This is set A, this is set B, this is universal. We want to determine the union. Intersection. A intersect B. The intersection, the points on common or elements in common are the points here between A and B. They belong to both A and B. And here we don't have any element, so here it's phi, the empty set, because we don't have elements in common. Those are disjoint sets. Disjoint sets. What about the third one? For the third one, A is inside B, so the intersection is the smaller one. Those are the points in common, because everything in A here, it belongs to B, but not every element in B here belongs to A. So the intersection is the smaller set. So A intersect B is A, the smaller set. And here, A intersect B is phi, or the empty set. Okay, now an exercise. If A is the set of all odd numbers between 0 and 10, and B is the set of all prime numbers between 0 and 10, we want to write the sets A and B using Grosser notation. So the set A is the set of all odd numbers from 0 to 10. The odd numbers are 1, 3, 5, 7, and 9. What about B? B is the set of prime numbers. What are the prime numbers from 0 to 10? The only even prime number is 2. So 2, 3, 5, and 7. Prime numbers are numbers that are only divisible by 1 and themselves. For example, 4 is not prime. Why? Because 4 can be divided by 1 and by itself, but it can be divided by 2 as well, so it's not a prime. But 5 can be divided by 1, can be divided by itself, but it can't be divided by any other number, so it's prime. So these are the two sets. We want to find the union of those two sets. Union means to put all the elements together in one set. 1, 3, 5, 7, 9. Those are elements of set A. And from set B we have 2. 3 is already taken. 5 already taken. 7. So we only need the number 2. Now what is A intersect B? The common elements. The common elements between A and B are 3, 5, and 7. So 3 elements. 3, 5, and 7. Now the third operation is the complement of a set. So if U is the universal set, A is subset of the universal set, now then the set of all elements in U in the universal set that are not in A are called complements of A and denoted as A to, and we have C above this A, so we write it this way, A to C, or to the C, and that means the complement set of A. Okay, now here what is the complement of A in the first diagram? What is the complement of A? Everything outside A is the complement of A. Everything outside A and inside U, the universal set, is the complement of A. As you can see here, all these the shaded region represents A complement. So this is A complement. Now what about the second diagram? A complement everything outside A. Everything outside A is A complement. This is A complement. What about the third set or the third diagram? Everything outside A is the complement. So this is A complement. Okay. Now we have some exercise here. We have universal set here, and we have set A. We want to find A complement. So A complement is everything in U, but it's not in A. So the number 1 is in U, but it's not in A. 2 is in both. 3 is in U, but it's not in A. 4 is in both. 5 is in U, but not in A. 6 in both. 7 in U but not in A. 8 in both. 9 in U but not in A. So the complement is 1, 3, 5, 7, and 9. Now we want to visualize it using Venn diagram. So this is U, the universal set, and this is set A. The set A consists of 1, 3, 5, 7, and 9, and we have some elements that do not belong to this set: 4, 2, 6, and 8. Now De Morgan's laws, we have two important laws. The first one is A union B, all complement is A complement intersection B complement. This is the first De Morgan's law. The second one, A intersect B complement, is A complement union B complement. So if we distribute the complement on union, the union becomes intersection, and we just distribute the complement on the sets A and B. And if we have intersection, the intersection becomes union, and we distribute the complement on A and B. This is called De Morgan's laws. So if we want to show this, what is A union B? A union B is everything in A and in B. A or B or both of them. So this is all elements in A or B or both of them. And then we want to find the complement of this. What is complement of this? Complement of this shaded region is everything outside this. Everything outside the union. So this denotes A union B complement. So this is the first thing. So this represents the left-hand side, for example, of the first De Morgan's law. And now we want to show that this is equal to A complement intersect B complement. So what is A complement? A complement everything outside A. This is everything outside A. Okay. And what is B complement? B complement is everything outside B. Everything here outside B. Now we want to find the intersection of those two sets, two shaded regions. What is the intersection of those two shaded regions? As we can see, if you try to find if we put them over, put B complement over A complement and try to find the overlapping region, that region will be, as you can see, A is not included and B is not included, and everything else is included in both of them. So this is the complement, A complement intersect B complement. And if you look at this, you find that's nothing but the right hand side of the first law. So those are equivalent. So this is how we show De Morgan's law. And we can do same thing for the intersection. The intersection complement. The intersection is this region. Complement is everything outside this. Everything outside this. Okay, this is A intersect B complement. Now, what is A complement union B complement? A complement is everything outside A. I mean outside this set A. So everything outside A is here. And everything outside B. Outside B, everything outside B is here. But as you can see, if we do that, everything outside A and everything outside B, that means we get this region. Okay. And that means the intersection, that region is this one. That does not belong to the, for example, to the intersection complement. So the shaded region is the A union A intersect B complement, and the shaded region in diagram 2 is A complement union B complement, and as we can see, those are equal. So that means the second De Morgan's law is satisfied. Now, if U is a universal set and A is a subset of U, what is A complement? A complement is phi. A includes everything, so it does not need anything. So the complement of this is phi. The complement of the universal set is phi. What is complement of phi? Phi is a set that does not have any element. What is the complement? It needs all elements of U to get the universal set elements. So it's U. The complement of phi is U. What is A complement complement? A complement complement is A, because if this is A, the complement of A is everything here, and then the complement of everything here is just A. A union B, A union A complement. The set union its complement. The set union the complement. That gives us everything. Everything is U. A intersects A complement. This is A, and this is A complement. So what is the intersection between them? There is no intersection. So the intersection is phi. Okay.